Hello everyone, I'm Shibaji Chakraborty from Virginia Tech, working under the supervision of Dr. Rohanami and Dr. Baker. Today I'm going to talk about sluggishness of the ionosphere. It's a characteristic time lag in ionospheric response to solar flares. So the outline of this talk is I'm going to first give a brief introduction and motivation of the study. Then I'm going to talk about the dataset and methodology I'm using. Finally, the result and discussion and conclusion. Solar flare is a sudden enhancement in the UV and X-ray bands of the solar irradiance. Um, so you can see it over here on the solar disk on the right hand side. These patches shows a sudden brightening in the UV and X-ray spectrum. These are the typically known as the solar flare. Also in here in the time series plot, you can see there is a sudden bump in the UV radiance. So this is also an example of solar flare. So all these figures are taken from SDO, AIA, and EV imagery, and the frequency here been labeled here 94 to 171 nanometer, and then 9.4 up to 33.9 nanometer. So in response to solar flare, we have a sudden disruption of HF radio waves traveling through the ionosphere, which is commonly known as a shortwave fade out. A typical signature of shortwave fade out is absorption, is the sudden increase of the attenuation in the HF signal that due to the sudden enhancement of the ionospheric electron density, which is mainly due to the enhancement in the X-ray and UV bands of the solar flare, of the solar irradiance. And here is the example given over here, which is DRAB model output that shows the sudden absorption sudden absorption enhancement in the different frequency spectrum. Uh, Other than the absorption, there is another phenomena we commonly talk about it. It's sluggishness, and commonly known as sluggishness is the delay in the ionospheric response to any change in solar flux. I'm going to discuss what is a sluggishness in the next slide. So, what is sluggishness? Sluggishness is the time delay between the maximum electron density in the ionosphere following the maximum flux during a solar flare. So that given by this particular equation, that delta is equal to time of electron density max minus the time of ionization irradiance max or irradiance maximization. So, however, people have found we cannot exactly measure the electron density at each individual point in latitude and longitude and height. So we use the height integrated method to find out what is the overall sluggishness is. So on the left hand side, sorry, on the right hand side, you see this red line going through this particular panel that shows the solar flux, and that black dots over shown over here, it's the rheometer measurement. And so you can clearly see there is a significant amount of difference in the peak of these two data sets, and that's commonly known as sluggishness of the ionosphere. And this is the height integrated data of the absorption. So we typically um, measure it as delta bar, not the delta. So that is the difference between the measured sluggishness and the default definition of sluggishness. So brief history and our current understanding about the sluggishness. When first Appleton described this phenomena, he found that it is inversely proportional to electron density and recombination rate at any particular height and latitude longitude as well. Sluggishness provides, he also showed like sluggishness provides some information about the ionospheric electron density and recombination coefficient. And later we found that recombination coefficient is also controlled by the atmospheric anions and the heavier cluster ions. People also showed like it varies linearly with solar zenith angle. And people only considered the soft X-ray peak from the solar wave band as a reference time to estimate this sluggishness. And it has a very complicated variation with height. Previous studies using VLF dataset reported a typical value of sluggishness between 1 3 to 10 minutes of sluggishness. Uh, so our objective is to use HF instrument to study HF absorption, demonstrate that the soft X-ray peak time can also be used as a reference, and do a variational study on the observations what we have found. So brief about what are the data sets we are using over here. Um, we are using rheometer. It's a ground-based system, passive radio system that provides the information about the HF absorption in the ionosphere by measuring the variation of the cosmic radio noise. Here is one example from the Ottawa rheometer station. It is a rheometer response to a particular flare on March 11, 2015. So you can clearly see the background radio noise absorption is typically around 0 dB, and whenever the flare hits, it jumps to almost 2 and 2.5 dB or something. So this is a typical signature of rheometer. One more thing, rheometer is typically operational around 30 megahertz, not exactly, but around 30 megahertz. So this particular absorption representative of a 30 megahertz absorption at 30 megahertz. So overall instrumentation and their locations. So in this study, we use all the rheometer station data from the station showed in this particular green dots in the map, and you can see it's distributed all over the Northern American sector, specifically in the Canadian sectors, and this red dash dot line shown over here, that's the longitudinal position of the GOES satellite, which is at the geostationary orbit. So first we talk about the correlation analysis of the sluggishness. What we did a sluggishness. Um, we 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 did the correlation analysis of sluggishness, which is delta bar estimated from the rheometer compared with solar zenith angle, and the first panel shows over here. Then we did the correlation with latitude, second panel, the local time, third panel, and finally the peak solar flux on the last panel. So we did a comprehensive correlation analysis of sluggishness from the rheometer measurement for C, M, and X class flare between 2006 to 2017, and we distribute or like divide the analysis based on C, M, and X class flare. As you can see, it's each row represents a particular flare type over here, and from left to right, the rows the left to right sorry each row represent a particular flare type, and each column represents solar zenith angle, latitude, local time, and flux. And the last panel over here that shows a generalized linear model that tries to predict the sluggishness or forecast the sluggishness based on all these four parameters. So you can clearly see there is a high positive correlation for all the different types of all different types of flare class. There is a high correlation with solar zenith angle and latitude as well, but a negative correlation with peak solar flux over here, that's shown over here. And finally, there is a kind of complicated, I would say it's a complicated variation with local time. It's not a linear one. And typically we understand the positive correlation with solar zenith angle and negative correlation with peak solar flux is due to the variation of electron density, and it's really easy to understand. If you think of a subsolar point or a peak solar dense lower peak subsolar point, if you go far away from the subsolar point, you have a less amount of ionization, and that leads to a higher amount of sluggishness. Similarly, if you have a lower class or like less amount of ionization irradiance, then you have less amount of electron density, that leads to a higher amount of sluggishness. So that's why you have a negative correlation with I infinity and a high correlation with solar zenith angle. However, the positive correlation with latitude, we think it's a variation due to electron density and somewhat the ionic chemistry around different latitude. If you go up in the latitude, the ionic chemistry not remains the same. As you go higher in the polar cap region, there are different types of chemical reactions, chemical kinetics going on, which is typically different from the mid latitude and auroral latitude phenomena, auroral latitude chemistry. So that's why we are not sure whether the positive correlation with the latitude is only due to the electron density. Now, finally, we talk about the sluggishness considering the hard X-ray as a reference, because typically, historically, whatever the study we found as per our understanding and our knowledge, the VLS studies only used um, this soft X-ray as their reference value. And we already showed it this particular figure on the top panel over here, where the red line is solar soft X-ray and the black dots represent the absorption from the rheometer for a particular event of March 11th, March 2015. And you can clearly see the different lines passing through. The red line shows the um, peak of the solar peak in the solar X-ray flux, and the black line shows the peak um, in the rheometer data. But what we did is, like, we also use the hard X-ray from the GOES X-ray sensor data to find out what are the peak value and the sluggishness estimated if we use that, like the hard X-ray as a reference data. So we found there is a significant amount of difference. So delta bar estimated from the soft X-ray is 46 seconds, whereas for the same event, the hard X-ray reference point provide us a 91, almost double the double of this particular value. So also in a recent, relatively recent study, YANSI find like the peak solar irradiance at different wave band during the solar flare occurred at different times. So referring to the ionization particular wave band, um, it's kind of complicated, because you never know which particular reference time you should choose to find out what is the delay in your in your data set. So we think, or we propose in a that way, like the correspond we refer to those ionization waveband which corresponds to the optical um, depth that produces the maximum absorption at that particular height. So that's kind of related to what we think we should take. And as you know, like all different heights have different all different wave bands or wavelength of solar irradiance have different heights as their optical depth. So it's a kind of complicated thing to choose. So it is related to which instrument you are using and where the response of your instrument is coming from. If you are using an active HF or a passive HF or VHF or VLF, whatever the data sets you are using, based on where you are getting the reflection from the ionosphere. So, okay, so taking all this together, here is our discussion and conclusion. So this is the first attempt, I'll let you know, this is the first attempt of characterization of sluggishness using rheometer, which is a HF type of instrument. Previously, people have done this with VLF studies, not with the HF instrument. So this is the first attempt of doing that. We statistically characterize the sluggishness observed from the rheometer. We find that it's anti-correlated with solar UV radiation intensity and positively correlated with solar zenith angle. And the reason being is it's enhanced electron density with higher radiation intensity. So as you as you have lower amount of intense radiation coming in, whether it's a form of less intense solar flare, or you are far away from the subsolar point, you have higher amount less amount of electron density that in turns produces higher um, sluggishness in your data. And it's positively correlated with latitude. We think it's definitely related to somewhat the electron density, but we also think it's somewhat related to the chemistry of the different chemistry variance with the latitudinal variability. And finally, we think like the sluggishness is estimated considering the peak solar zenith angle till date, but we clearly demonstrate that we can also consider the hard X-ray as hard X-ray reference data to find out what the sluggishness is in your data, and the estimation change significantly in that case, almost doubles. So peak and we think the peak solar radiation is at different frequencies during different solar flare occurred at different time, so that leads to these type of different solar zenith angle sorry, solar sluggishness estimate. Okay, so that's all. Thank you. Any question and comments? Also, I have submitted a manuscript to JGR Space Physics. Thank you.